another panel. So this is the third panel, and you can see the list of panelists listed here. Do want to remind everyone that if you have, hopefully you've watched the presentations beforehand, and if you have any questions at all, please put them in the Q&A so that we can have the listing of them. And then I think we will start here by having each of the panelists, in order of how it's on the screen, introduce themselves, and they can give sort of a 1-minute summary of their talk so that you're all reminded of what they were talking about in the pre-recorded videos. So I think since we are a little bit behind, we can just kick that straight off. So I would say, Philip, please go ahead.
Hello, can you hear me?
Yep.
Okay, yeah, so I'm Philip Nekansky. I'm a postdoc at DAISY Hamburg, and I made a presentation on the multi-boson production measured at Atlas. It's sort of a summary of large variety of measurements, combining standard model searches, precision measurements, and some real standard model interpretations. So, for example, I showed 4-lepton differential measurement, d vector boson scattering in ZZ plus 2 jets final state, and also some photon-photon interactions, namely the gamma-gamma-2 WW observation.
Okay, very good. So then next up we have Julia.
Hello, everyone. I'm Julia. I'm a PhD student from University of Trieste, Italy, and I presented multi-bosons results from CMS with a special focus on cross-section measurements and limits and anomalous coupling in the effective field theory framework. And I focus on some latest results like the W gamma gamma, WZ, W plus gamma analysis, and a special analysis of diboson cross-section at the special energy of 5.02 TeV. Thanks.
Thank you, Julia. So then next up we have Sasha.
Hi everyone, I'm Sasha Tomalak. I have finished PhD and had a postdoc position in Mainz working on other subjects than I talk today, on low energy proton structure with emphasis on radiative corrections and two-photon exchange. And this previous work was motivated by the proton radius puzzle, but then I switched to neutrino physics. And now I'm postdoc at the University of Kentucky and work very closely with Fermilab. And I'm working now mainly on radiative corrections and neutrino interactions with electrons, quarks, protons, neutrons. And my talk will be the first full and consistent formulation of radiative corrections to neutrino nucleon scattering at GeV energies of beam. Thanks.
Thank you, Sasha. So then Paolo.
Yes, hi, I'm Paolo. I'm from Pisa. And I gave a presentation on the possibilities of precision electroweak measurements with the FCCE program. So starting with precision measurements at the Z-pole, and then essentially precision measurements with multi-bosons at higher energies. So ranging from the W pair threshold up to the top pair production at 365 GeV of collision energy, and that's what it was. Yes.
Okay, thank you, Paulo. Then Randy, please go ahead.
Yes, hi, I'm Randy Rupti. I'm a faculty member at the University of Notre Dame, and I represent a group called Radical, and what we're developing is radiation-hard electromagnetic calorimetry. Our emphases are really directed toward FCCHH. It could also be for E plus E minus machines or other machines as well. The idea is to have electromagnetic calorimetry that's ultra dense and ultra fast so that you can not only measure energy in a very short distance of the order of maybe 12 centimeters or less, very small mollier radius, and also measure the timing of the EM shower. And we're striving for 10 picoseconds there, but it'll remain to be seen what's going on from beam tests. And my talk describes some of the techniques we're using to work on this calorimetry technique. Thank you very much.
Thank you, Randy. Okay, then next up we have Samuel.
Hi, I'm Sam. I'm a postdoc at Harvard. The work I was presenting was on doing fits to standard model EFT coefficients, global fits to Higgs, diboson, and electroweak precision data. But then in particular, kind of interpreting those fits in the context of simple extensions to the standard model. So we considered a couple very simple extensions to the standard model with extra singlets, extra Higgs doublets, or vector-like quarks, show what kind of patterns of coefficients you can generate and how the global fits kind of inherently constrain these models. Thanks.
Okay, thank you, Samuel. Then next up we have Simirai. I hope I pronounced
Hello, can you hear me?
Properly. Thank you. Yes, we can hear you.
I have a problem to hearing you. I don't know why, but I can hear you very discontinuously. Okay, so I'm Semirai Girgisçaylı. I'm a research scientist at Boston University and an experimental physicist at CMS, working for Standard Model Physics Group. In this group, I'm searching Z boson production in electron and muon decay channels. In my talk, I presented recent vector boson and jet measurements from the CMS experiment. Particularly, I focused on Z plus jet, W plus jet, gamma plus jet, and also vector boson plus heavy flavor measurements.
Okay, very good. Thank you. Then last we have Yasser. Please go ahead.
Hi. Okay, so I'm Yasser Ronell, professor of physics at University of Iowa. And the talk that I've prepared was new radiation harsh scintillator for FCC detectors. Basically, scintillators are very important components of any detectors in high energy physics, including the intensity frontier. So here we described very hard scintillators that we studied, radiation damage studies, as well as production and test beams at CERN and Fermilab. And also we developed wavelength fibers that this kind of scintillators, one of them is our own product scintillator X, radiation hard, very hard, up to 40 megawatt. So we hope that develop these ideas and they use them in the future FCC type of detectors.
Okay, very good. Thanks. Thank you, everyone, for the introduction. So now we have a good amount of time remaining for questions. So please, post any of the questions you have in the Q&A. Make sure to mention who the question is for, and then we can go through those. So there's already one question that came through Slack, which is for Philip. So the question is, could you provide some more details on how you estimate the pileup background in the Z-gamma analysis? And how is it compared to the other main backgrounds like jet to photon and electron to photon misidentification?
Yeah, that's a great question because I think that's a really interesting part of this analysis. Sadly, I don't have too much detail in the backup. Maybe on page 6, if you could of the backup. No, sorry, a little bit farther. The backup then has its own numbering, but yeah, the contribution in general is quite small. So depending, here on the plot on the left, you can see basically the percentage of this background depending on the average number of interactions we have. So for over the whole data set, the average is around 35. So the contribution overall is around 4%. As how this is measured, basically the main separation between the pileup and the primary interactions is in Z, so along the beamline, and you measure how these photon events, which are separate from the dilepton events, behave farther away, where you can isolate them quite nicely, especially if they contain a track from conversion. And then you basically extrapolate from that, let's say, tail region into the signal region.
Okay, very good. So hopefully that answered the question for whoever asked it. If there's a follow-up, you can post it in the Q&A again. Okay, so then there is another question that came in through Slack. This one is for Sasha Tomolak. The question is, how are the EM corrections from lepton-nucleon photon exchanges impacted by the nuclear medium? Are coherent effects important?
Yes, it's a very good question. First of all, I would like to say that up to now, we did calculation only on free nucleons without simulation of nuclear medium. That's why this answer right now on qualitative and quantitative investigation. But what I want to say is that the first thing to mention that usually how people simulate this event, they use factorization. First, what's going on nucleon level, and then what's going on in medium. And basically, my work will provide inputs for nucleon level, what's going on nucleon level. I think that's the answer.
Okay, very good. Okay, so right now there are, I don't see any open questions. I think also if any of the other panelists have a question, you can feel free to speak up now. I think this would be a good time. Otherwise, I can ask a few questions as well.
Yeah, this is Ian. I have a question for Sam Hommler. In particular, on slide 16, he shows the effects of a renormalization group running and how it affects the constraints on type 1 and type 2 Higgs doublet models. It looks like the RGE running matters more for type 1 versus type 2. Is there good intuition as to why this happens?
That's a great question. I'm not sure I know the answer offhand, but I would guess that these limits, so let me see. I mean, the RGE running is changing all of these things, I guess, as a function of scale. And so it's probably just a matter of the Yukawa couplings that are being modified. I guess if you're modifying the top Yukawa, then you know, a smaller difference will make a bigger impact on the fit. And I guess it's also the bounds in the type 1 are looser, I guess, right, in terms of the alignment parameter. And so I think the effects of the running are also kind of proportional to that. So I think it's just because the constraints are looser, you get larger effects from the running, and it makes a bigger difference on the fit.
Okay, good. Thank you. I think I can see that. And then on the previous slide, on slide 15, you have this yellow line for type 1. What did you choose for tan beta, and why didn't you vary it for the type 1 on the left-hand side?
Oh, that's a great question. My guess is that it's tan beta equals 5. We were just picking arbitrary points. I think as you change tan beta for type 1 versus type 2, it would sweep out kind of the whole ellipse in that plane, I think. I mean, you can see how it changes from tan beta 1 to 5 for the type 2.
Okay, so you expect something similar for type 1 that would just start.
Yeah, exactly.
Good. Thank you.
Thank you.
Okay, so thanks a lot for that question. In the meantime, there was a Q&A question that came in. So this one is for Julia. So the question is, as I recall, W gamma production has a process called the radiation amplitude 0. Do you know if this process can be observed at CMS?
Oh, maybe I can follow up on Slack because I need to check. Yeah, this process can be, this is a process that we have in W gamma production, but I need to check if there are some measurement by CMS in this channel.
Mm-hmm. Good. So yes, so for the person who asked the question, you can check on Slack for a follow-up there.
Yeah.
So that's good. That's why we have Slack, right? And it's so we can have some more further communications. there any of the other panelists who have a question for any of the current panelists? So we have another good 10 minutes or so. Okay, so why don't I ask a question? Let's see. Maybe I'll go to Yasser, so a little bit on the hardware side. I noticed in the slides there was some mention of the LED stimulated recovery, and I was wondering if you could explain a little bit more about how that process kind of works.
Yeah, sure. Basic idea here is that we just noticed that we can really stimulate the recovery using this technique. So we have built a small electronic device which flashes LEDs. Basically, we put three colors: red, green, and blue. And this is attached to basically to scintillator before we put this in the radiation area. Gamma source or proton source, we tested them. And then after the irradiation is done, we saw that obviously damage on the scintillator. Putting this device and waiting a couple of days, and you can see that most of the recovery, there's a natural recovery on scintillators after we take out the radiation area. But this really increases very, very fast, this recovery. So for example, instead of 10 days, it is just 1 day, some of the results that we presented. So this is very encouraging. So for the future experiments, when you build scintillators, and obviously you know that in very radiation difficult areas, they will be damaged. But when you have this already attached to your scintillator, this very tiny device, and will be doing recovery simultaneously.
Mm-hmm. Yeah, that sounds really cool. Do you know how the sort of what the underlying physics process is that makes it go so much faster?
I mean, basically, there are many ways of have the recovery, with natural recovery, or you can sometimes heat materials, and there are many ideas that have been developed before. But this is that with this three lights section, we can really attack the basically color centers related to the scintillator wavelength emission. So blue, green, and red. So some scintillators really in blue nature will be really recovers quickly with the blue simulation of the LED.
Yeah, it makes sense. Yeah, it's a cool idea. It's nice that it seems to work.
Yeah.
Okay. Thank you, Yasser.
Okay, Nadia. Thanks.
Yeah. So in the meantime, we did get another question in from Slack. So this one is for Randy. So the question is, the overall performance of the new design to be red heart sensors looks good. How much does the degradation from radiation damage affect that performance? And is there an intense enough test beam to let you test the actual conditions of years of running in the real experiments?
Okay, so that's always a great question, and one that's perennially out there. We have ways of testing with high fluence radiation dose, which is done with gamma rays. We also do proton and neutron exposures. Those are principally done at Los Alamos or at CERN. And the complication there is that the radiation doses are applied in a relatively short time as opposed to a much lower dose rate over a longer time. One can try to model those things, but again, in many cases, the most egregious doses occur slowly, so the dose rate is low, but it accumulates over time. So what we're trying to do is to work with materials that are radiation robust as they can be. Organic materials tend to be the most sensitive here, but if their dimensions are very small, short, then the impacts can be small. So in shower max timing, those potentially fragile filaments might survive just fine, and that's driven by the radiation survivability of the fluorescent dyes as opposed to optical transmission through materials. For more robust and more intense radiation regions, then we're going to want to rely on inorganic materials. And there we're hoping that ceramics and crystalline materials and perhaps quantum dots and glasses will be the revolution that allows us to make progress there. There are beam tests coming up and there are radiation tests coming up, but for most of us, and probably for those of you too, those have been slowed thanks to the COVID situation. And so it's much more difficult. Also, just as a humorous anecdote, if you dose something to a high rate, then in its hadrons, then you have to wait for it to cool down before the laboratories release them to you so that you can actually measure again. So it's a combination of interesting factors, but the goal is FCC-HH operation. So that's the intention. Thank you for the question.
Thank you, Randy. Yeah, at least for that target, there's still a good amount of time.
Yes.
So that's a good thing. Okay, so let's see. Currently don't see any open questions in the Q&A. As always, if anyone has one, please put it in there. So maybe I can ask a question to Semirai on the Z plus jets measurements. It seems that the existing description, the description of the jet multiplicity spectrum in the existing Monte Carlos doesn't seem to be too spectacular. Do we know sort of why that is or where any improvement may come from? It seems that the W plus jets is better described than the Z plus jets. Maybe okay, did she drop? Looks like maybe she dropped out. I do not see her connected at the moment. Okay, well, we can come back to that. If she is no longer connected, she seemed to have some problems. So then I think, because nobody has asked the question of Paolo yet, so I'll ask a question there as well. So at the FCCE, we'll have lots of higher precision than we currently can reach. And I was wondering if you could comment a little bit on what sort of new things we can probe with that in terms of, let's say, VSM physics models.
Hi, yes, thanks for the question. Yeah, I think, I mean, it's hard to say exactly, but you can see, like in the summary slide, right? This in terms of the Electroweak fit, what the opportunity here is to have a precision improvement of a factor 100 or so. So it's really something that really is a huge jump, right, in precision that will definitely. And okay, we have studies, for example, in terms of EFT coefficients, and we see similar improvements, right, in that direction. So the potential is really that is something like a factor 100 in probing possible new physics scenarios from this precision point of view.
No, definitely, it's a major jump.
Yeah. I mean,
yeah, I guess it's also up to the whole community to try to understand what all we can do with this extra precision, and what the impact would be, if we do find a deviation in any of these precision measurements.
It's hard to predict, right? I mean, it's
exactly.
Until
we see something, it's always hard to know.
Yeah.
Definitely. Okay, are there any final last questions that anyone may have? Either directly to the slides that were posted before, on the presentations posted beforehand, or on the general topic that the panelists talked about. Otherwise, it looks like we've made it to 11:30 Central Time, which was the scheduled end of the day. So I don't think we need to drag it out any longer. These conference weeks always end up being quite busy for everyone. So I'd like to just thank all of our panelists again for preparing the presentations beforehand and for being here to answer any questions. And also thank you to the attendees for coming to listen, for listening ahead and then posing your questions. I think it's So it's interesting to try out these different formats in our Zoom world these days. So I think that's very good. Yeah, so thank you, everyone. And make sure, use the Slack if you have any follow-up questions. I'm sure people, the panelists will monitor that, or the organizers can keep in touch with the panelists if there's questions that pop up later.